Hey folks, so today we will cover a practical demonstration of VLLM. So this video is going to be a continuation from my previous video where we talked about VLLM in a theoretical perspective. So we covered a lot of points here, right? How do we see performance difference with VLLM? How does continuous batching works with VLLM and many other points. So you can go back to that video if you want to understand more about VLLM from a theoretical point of view. I would actually recommend that first and then come to this video if this is the first video. And then we have provisioned two different GPU machines here. Both of them are exact same spec, but just in different geolocation. One ends with public IP .87, another one ends with .115. So to be in this situation, all you need to do is clone my repository. After you clone my repository, the only command you need to run is, for instance, let's say after you have this cloned, all you have to do is go to GPU. Just go to my home directory, go to GPU VAS AI, and then there's Kubernetes single node setup, and then run all.sh. That's one script that does everything for you, so you'll have a working Kubernetes cluster. So if I go kubectl get pods -a, you can see I have a bunch of pods running. There's a single node setup, right? So just to let you know, there's only one node in each cluster. Kubectl get nodes. There we go. There's only one node, right? So in one machine, what we will do is we will go the normal container way. In another machine, we will go the normal VLLM way, and then we will see how do we tweak those things and what kind of differences do we see in performance, right? So let me okay, so the machine on the top here, this is curl as full if config.me. If you run that, you get a public IP. So it's this machine here .87, and then these two bottom two screen are gonna be the other machine curl as full if config.me, and it's a typo there, if config.me. Okay, so this is .115, right? So it's this machine here. Bottom two screen is one machine, and then this top two is another machine. So now to get our setup ready, what we need to do is you need to be in, let me actually go back to the proper directory. So go to the VLLM directory. Once you're here, you will notice there are different Docker file that I use to create an image. So if I look at the Docker file, it's a very simple image actually. I'm just getting the latest image from VLLM OpenAI. And just to let you know, this image is actually a massive image, right? So you see that it's 13.04 gigs, but that's a compressed size. When that image is decompressed, it comes out to be around 20 to 25 gigs. That's just the way the VLLM image is. I haven't looked deeper into how to compress that image as of now, but if it takes a long time to download that image, that's the reason, right? Because the base image itself is much bigger. And then there's nothing else major here. So let's go to our Kubernetes directory. You will see I have a config map, I have a deployment, and then I have my service.yaml. So if I look at my config map.yaml, there are a couple of things I have defined here. So what kind of precision we want to use, the D type, right? We've been talking about this quite specifically. So if I go to Hugging Face, and you'll see, depending on the model that you want to use, you will see the D type for that. So let's have a look at the Quen 2.5, and then you will see that it's a BF16 model, right? So I've just mentioned that by default, and then just mention the model ID, and then the GPU memory utilization and the max model length flag, right? So the reason we mentioned this on config map is that, for example, if I want to use a completely different model, then I can just come here and change this in my config map. That's it. So do this, do kubectl apply -f config map.yaml. After we do that, we need to create our service as well. There's a typo in my service. I'll fix that in my next git push. Kubectl apply that service.yaml. Okay, so I have my config map created. Again, if you are new to Kubernetes, config map is just a way to store a variable in Kubernetes, store it once, reference it from any location. That's it. And then after that, we have our service created as well. So let me go ahead and run kubectl apply -f deploy.yaml. So this deployment will create a pod, right? So what we can run here is that we can run the watch command, and then we can run kubectl get pods. So we will see if it's creating new pods or not. And actually, let me just grep for the pod that I want. So put that in quotes. kubectl get pods, and then grep VLLM. Okay, so this is the container that I'm worried about. I don't care about any other containers. That's why I have that watch command. And if I run a real quick kubectl describe pod, you will see it's still downloading the image, because as we mentioned, the image is a massive image, right? So pulling image, this is going to take some time because it's more than 25 gigs. So let's go here and let's make the normal container setup for this. Just go to container GPU, and then you can see, so here this is my own image. So if I go to Docker file, again, this is not a massive image. This just downloads. This works in Ubuntu. You know, it's the image size is not as big as the generic VLLM, but then there are a few buffers. You know, there are a few other things that I've added on this image to make this work. So for this to work as well, just go to Kubernetes, and then you'll see the similar stuff here. There's a config map, there's a service, and then there's a deployment. So let me run the same command here. It's going to be watch kubectl. Let me actually see what is named in the deployed pod is named HF, that's inference. Okay, so let's run a watch command, and then let's go kubectl get pods, and then let's grep for HF. So there's no pod right now, we know, because I haven't created any. So let me, and then if I have a look at my config map here, it's a very simple config map that just has the model path. So changing the model path to, you know, any public Hugging Face model ID will change our model. So that's a nice and easy way to, you know, work with different models, right? So let me go ahead and run the command kubectl apply -f config map. After my config map is created, let me create my service. Okay, my service is created as well. So let me go ahead and run kubectl apply -f deploy.yaml. Okay, so now this should create a pod, and we see the pod has been created. So let me run a kubectl describe pod on this one. So this wouldn't take as long because the you know, the image is not that massive, right? So the image here is about 7 to 8 gigs compared to the image here being 25 gigs. So we need to wait until the container creating task is complete. So once that is completed, then we have you know, then we have a VLLM pod, and then we have a normal container pod, right? So the top two screen VLLM, bottom two just normal container. Okay, so while that is in progress, let me just have a look at model interaction.py. So as of now, I've just, you know, I just have some curl request, and that's how I interact with my model. So I will create a port forward so that I can use my localhost IP on port 8000, and then I can just run curl command on the API endpoints, and that's how I interact with the model. So same here as well. That's the way I interact with the models. And then we will change different flags like the number of max tokens and so on, and we will see how things behave for different token size. We will see how long the response takes to come as well, and then we will see the GPU utilization. So let's go here and run NVIDIA that's SMI. So we know there's nothing going on in our GPU because we're still building the container, and then still on container creating stays. Okay, so we just went running here. That took about you know, 4 minutes, so that should take probably a few more seconds. Okay, let's have a look here. So you can see that my VLLM container is on a running state, right? But my GPU memory and utilization is still nothing, right? No utilization yet because we haven't interacted with the pod. And once the pod is ready, it needs to download the image as well, right? So that's going to take some time. So if I run watch here, we will see that it will start occupying the memory. There we go. Okay, so it occupied the memory. It has now 6.5 gigs, but that is going to go up as well, because if I go here, if I go to CD GPU Vast AI, and then if I go the VLLM way, okay, let's go to the Kubernetes, and then let's look at the config map, right? So in my config map, what I've said is that I want to utilize 0.9, meaning 90% of the memory that's available for my VLLM setup, right? So as soon as I start interacting with the model, that memory utilization is going to go up to 90%, right? It does not mean that it's actively using that 90% of the memory, but that's what it's claiming at, right? But here, so okay, now we have this running as well. If I have a look at watch NVIDIA-SMI, so if I have a look at my NVIDIA-SMI here, I see there's 8 gigs of memory consumed, because we know this is a 4 billion parameter model, right? So when this is this is a 3 billion parameter model, so that takes around 6 gigs, right? And then there are other runtime dependencies which consumes roughly 8 gigs. So but here it's already consuming 23 gigs, so see the difference already, right? It's the exact same model. So if I'm here, let me go to cd GPU VAST AI, and then this is container GPU, and then let me go to Kubernetes, and then let's go config map. So see the model path, it's the exact same model, but the memory utilization here is 23 gigs and here it's 8 gigs, right? Because, you know, we define the model, if you look here, we define the GPU memory utilization to be 0.9, right? That's why it kind of pre-claims that 90% of the memory. That's why you see something of that size, and then you see something, you know, of that particular size here. So that's the difference, right? That's number one difference. And then, okay, so let's interact with the model, and then let's see how these things differ. Okay, let me just scroll this down a bit, and then you can see here, right, my utilization is 0%, same here as well. The only thing different is the memory being utilized. So let's interact with our models and let's see what kind of differences we see. Okay, before I do that, I need to do the kubectl port forward. So that, I mean, I don't necessarily need to do kubectl port forward. I could just work with the service IP, but you know, I just find this to be an easier way. And then, so let's just send that in the background, and let's have a look here too. Cat model interaction. Okay, kubectl port forward, and then that particular service, and then let's send that in the background as well. Okay, so kubectl get service. Okay, HF info service is there, and then VLLM-API. I just need to make sure my service are there, VLLM-API. Okay, so now we should be able to send curl request on our local IP, because we just did a port forward saying that any request coming to that particular service on that port can be forwarded to my localhost on port 8000, right? So this one being VLLM, let's run the curl request. Okay, so let me run that, and then see GPU utilization went up to 92%, right? And then in less than 2 seconds, I got my response, right? So my query was, if we want to have a look at my query, it was just like, you know, give me the, I think, list 30 CDs, that's it. But then I gave max token as 200. So if I increase the size of the token, I will probably get my full response. So let me just go to 300 tokens, and then let's, sorry, let me run the query again, and then we will see the, okay, now we see 30 CDs because we increased the number of tokens, and then our GPU utilization went up. Sorry, the time was 3 seconds for the total inference, right? And then if we want to have a look at the GPU utilization, so let's have a look again, and then we see 93% GPU utilization. Memory doesn't change as much because, you know, it already has enough memory that it needs. Takes 3 seconds to give the query, right? So let's have a look here on a normal no VLLM setup where I will ask the exact same thing. So the query is gonna be exact same, list 30 cities, max token is 300, and then let's have a look at the GPU utilization. So, okay. See, okay, let's go. Okay, so it took 15.6 seconds, right, to complete this. And then it didn't actually give us Okay, it gave me answers in 300 tokens. It's not something that we were kind of expecting, but it did give me the answer. But then the GPU utilization didn't move, right? So let me just ensure that I have the right cell here. Curl that's flow if config dot me. Okay, so this is 95. Okay, so let me run something somewhere here. Okay, it's 95 as well. And then let me run watch dash n 0.1 nvi via dash smi. Okay, so we see the VRAM here, and then let me run the query again. So okay, there we go. We see the utilization now. So the utilization is at 28% compared to 90% here. And then see, it's taking much longer to complete the exact same query, right? It's still kind of requesting the query. But if you look at the VLLM way, and it took 15 seconds, right? So now doing the VLLM again, we see the GPU utilization goes up to 93%, takes 3 seconds for the exact same query, right, to answer. But here it took 15 seconds, and then the GPU utilization never went up, right? It never went more than 23%. So that's a big problem, isn't it? Like the GPU, you don't essentially optimize your GPU utilization. That's very, very low, and then it takes much longer for inference, right? So why does this happen? This is because of how VLLM works, right? Like it does a continuous batching of requests, which we kind of talked about here, right? So what it does is that, you know, for instance, it has like, instead of running like small kernels, small function, like one function at a time, it collects all the functions, right? And then it runs it at the same time. And like, instead of doing small jobs, it runs it as a big job, right? But in this particular situation, what we can see is that I only have one job going in at a time. So it's not multiple requests. But what's happening is that, you know, VLLM is optimized in a way to interact with the GPUs in a much better and faster way. It has optimized CUDA kernels. It's built for like a better utilization of GPU. It's built for high throughput. We saw all of those things, right? So if you really want to go into the theoretical side, I'd recommend watch the previous video. But here, you know, we see the real difference, right? So when does this come handy? So imagine a situation where you have, you know, as of now, I only have like one curl request that goes to my model, right? But imagine a situation when you are serving your model, and then, for instance, you have like multiple customers that are requesting this model, right? So in this situation, let's imagine just me sending a curl request to my model, right? And then my response time is like, say, 15.5 seconds. Now, imagine when you have like multiple customers, right? So what if you have like, you know, 4 different customers hitting the model? Now what happens is all of these requests are going to take more than 15 seconds because it needs to wait in the normal container way, right? It needs to wait until that request is complete, and then it moves on to that, and then that, and so on. So imagine going to ChatGPT and then your wait time is probably 60 seconds. You would not interact with the model at all. And then for you as a, as someone who's hosting that model, you see that your GPU utilization never climbs up above 20%. That's why your request has not been completed fast enough, right? Like the GPU has the potential to complete the request fast enough, but just your setup is in a way that it never fully utilizes the GPU, never utilizes the memory in a better way, so that it's very, very slow to get this request completed. But now imagine it's VLLM way. What happens is instead of running one request at a time, you can run a live batch of requests, right? So all of these 3 requests go to my model at the same time. So there is a thing called lanes. So we talked about how do you set the maximum number of sequences, the maximum number of live requests that VLLM can handle at the same time, right? So based on that, we can say that how many requests can be actively served by the model at one time. So in this situation, what happens is all 4 requests will be handled by the VLLM at the same time. So instead of instead of 15 seconds, we're down to possibly 3 seconds, or maybe 4 seconds or whatever. But it's much better than having 15 seconds, right? So this way, then you have better user satisfaction, and then if these 2 other users are waiting as well, it's not a longer wait, right? Like getting your response in 3 seconds, it's okay. It's not a big deal. So I think that's why all the big production ML servings, now I see the reason why you would go VLLM, because it just makes sense, right? Like you don't want that low GPU utilization, you want an active GPU utilization. So yeah, I think that's one of the main difference of VLLM. And actually, let me make some config changes, and then let me show you what happens with certain changes here. Okay, so let's go to VLLM Kubernetes. Okay, so let's go to config map. Okay, so see that GPU memory utilization? Let me change that from 90% to maybe 80%, right? Okay, and then max model length. So max model length being 8192, what I'm saying is that the max token that I can get reply is going to be 8192 for one query, right? It will not cross that particular value. So I don't necessarily need like a bigger value like this, but it's just what's there by default in my situation. But I can absolutely decrease or increase that value depending on my token, right? So let me change that to 0.8, and then I can change the max model length to probably, let me just change that value to 4192. It doesn't have to be in 4192, like it can be 4000 if needed, so, or 4002. So let me save that. So now what I need to do is I need to get my config map, delete das f config. I'll delete the previous config map, and then I need to recreate the new config map. Apply das f config map dot. Okay, so my new config map is created with the updated value. So now let me actually delete my part as well. kubectl del delete das f deploy.yaml. Okay, so my VLLM part is deleted. We see the memory went down to 1 megabits. So let me go ahead and run kubectl. Actually, I'll just delete my service as well, because kubectl delete -f service to YAML. I just want to build it up in a clean way. That's why I'm doing all of these deletes. So kubectl -f apply -f service to YAML. Okay, service is created. And then let me recreate my deployment. Kubectl apply -f deploy.yaml. Okay, it's not gonna take as long as it did to create the parts, because we already have that image, so we don't need to download that 25 gigs image, right? So it's not gonna be as long as how it took before. There we go, it's already running. So we'll see that occupying the memory here straight away. And then let me run the port forward again. Okay, it says ss-tulmp. Okay, I see I'm already listening on the port. ss-tulmp, and then prep for 8000. So this means like show my sockets, and then show me my UDP ports, TCP ports, and then like show me the port flagging. Yeah, it's different flags, TCP, UDP, and then that's ports. I forgot what LN exactly meant, but it's a way to see what process is using. Like it's the way to see your current port utilization in your Linux machine. Okay, so we're up to 6 gigs. So we see the model weight is loaded. Now let's see the difference it makes because of the GPU utilization value being changed from 0.9 to 0.8. So it should not consume around 23 gigs that it consumed before, right? So do we have that output somewhere? No. Okay, but anyways, see, we saw that value was close to 23 gigs, right? Because we used 90%, but now since we're using 80%, it's not going to cross 20 gigs. So let's have a look at what kind of difference does it make then in terms of interactions with the model, because for these previous query we saw it took 8 seconds, sorry, it took 3 seconds, right? So okay, oh wow, it actually took even much quicker. It took 0.06 seconds to complete that. Okay, syntax error. Okay, let me go here. Oops. Okay, so it's the exact same query, right? The same model, and then there's 30 cities, 300 tokens. The only changes we made was on our max sequence size, we reduced it down to 4,000. So that means we have many more lanes rather than having 3 or 4 lanes, right? That's why I think the request is getting much faster. And then we see the memory utilization is 20, and then let's go. Wow, literally not even a second. That is insane. Okay, let me change my token to 3,000, and then let's see how long it's going to take for a 3,000 token request. Okay, so the max token list 300 cities. Okay, let's do that. Wow. Okay, so list 300 cities, and then it gave the answer in 3,000 token. Okay, it didn't necessarily give the answer that I was looking for because the model is a bit different. It's an instruct model, right? So let me actually maybe change my query. Sorry, blog. Okay, sorry, block 2 pages at least. And there we go. Okay. Okay, this is something different. Even though I'm asking it to give me, for example, if we look at my query here, I'm asking like, give me an SRE blog for 2 pages at least. But still it's giving me the cities. So something is happening here that the model is just responding whatever the previous value was. Okay, so this is not expected. Okay, yeah, I think I'll have a look about that in the next video and then see why something like that is seen. But I think the point here was to see the better and efficient GPU utilization. We know why the memory utilization goes up to a certain number. We can absolutely configure that based on the value here. We can change the max model length to ensure that how many, like what's the max number of replies that we want in terms of token. And then VLLM is significantly faster than our normal container setup. So yeah, that'll be all for this video, and thank you for watching, guys.